So today we're going to discuss the procurement and considerations of the construction commissioning for wastewater capital projects. I just wanted to give you an overview of where we are in the region of Waterloo. We're located in southern Ontario with a population of approximately 537,000 people, and it's approximately an hour west of Toronto. We are a two-tier municipality, including the three cities of Waterloo, Kitchener, Cambridge, and four townships of Wilmot, Wellesley, and Woolwich and North Dumfries. The region operates and manages 13 wastewater treatment plants and 6 pumping stations, 2 regional collection systems, and there are 5 receiving streams in the area. The region's 10-year wastewater capital budget is approximately $600 million with an annual O&M budget of around $90 million. The case study will be around the Kitchener Wastewater Treatment Plant, which is one of the largest wastewater treatment plants in the region of Waterloo, with a rated capacity of about 122,000 cubic meters per day and an average flow of 70,000 cubic meters per day. The existing treatment process includes headworks with screening and grit removal, followed by primary clarification, and splits into 2 plants, plants 1 and 2. It is further treated using secondary treatment with aeration, fine bubble diffusers, and high-speed turbo blowers. The effluent is treated with UV disinfection and is discharged to the Grand River via an effluent pumping station. The plant is also located in a floodplain. Ferrous chloride is added at the primary clarifiers for phosphorus removal, and waste-activated sludge is thickened at the primary clarifier. The primary WAS is also co-thickened and is anaerobically digested and stabilized, and is then dewatered with centrifuges that are located approximately 2 kilometers from the plant and is disposed off-site by landfill. The region completed a wastewater master plan in 2007 and approved by a regional council. At that time, the budget for the 3 of the larger wastewater treatment plants in the region was about $446 million over the next 10 years. Region had looked at 3 different types of delivery models for these upgrades: the design bid build, and the construction manager at risk. The region was looking for potential opportunities for accelerating project schedules and reducing the overall cost to deliver the projects. The recommended approach ended up being design bid build, which is fairly typical. More information about these models could be provided to you offline if you wish. As mentioned, from the region, the wastewater master plan was established in 2007, and I was the project manager at the time for the detailed design and construction phases of the Kitchener wastewater treatment plant upgrades from 2008 to about 2015. And then I moved into my new position as head in environmental engineering. The objectives of the upgrades was to improve the effluent quality of the discharge to the Grand River watershed and improve reliability and energy efficiency, address odor concerns by decommissioning the biosolids storage lagoons, and upgrade the standby power. The project was phased in 3 different phases as shown here, phase 1, 2, and 3, and then I'll go into those phases in a little bit more detail. So the first phase was the biosolids dewatering facility, which was constructed in 2012, and the cost was about $23 million. The consultant that we retained for the design and construction services, contract administration services, was Hydro Mantis and Tetra Tech, and the general contractor was Graham Construction. Here are just some photos of the biosolids dewatering facility. This was a retrofit project which had an existing sludge transfer station, and there was a new building that was added to the station, and it housed the 2 new centrifuges, cake hopper, and then transferring the biosolids to load into trucks for off-site landfill disposal. The second phase was the upgrades at the Kitchener Wastewater Treatment Plant, which consisted of the UV disinfection and effluent pumping station, and also Plant 2 aeration upgrades. The project was completed in 2013, and the cost was approximately $39 million in capital. The consultant for the detailed design and construction administration services was CH2M Hill, and the contractor was King City Group. The region received FCM funding for the Plant 2 aeration upgrades, which consisted of replacing old aging mechanical aeration equipment with fine bubble diffusers and high-speed turbo blowers in order to improve the plant effluent quality discharge to the Grand River. Also, the existing chlorination disinfection system was replaced with a new UV disinfection, and a new effluent pumping station was constructed to improve the discharge to the Grand River. There is also a link on the FCM website about this case study if you wish to read more about it. The Phase 3 Kitchener upgrades, we had retained AECOM, the consultants, for doing the pre-design, the detailed design, and the contract administration during construction. In the planning and detailed design phase, we looked at options to complete all the upgrades under one contract, or splitting the projects into multiple contracts. The recommended approach was to separate the upgrades into individual contracts based on process and location. And we were able to look at and view these contracts and stage these contracts in order to ultimately meet the goal of completing all the upgrades in addressing the effluent water quality by 2018. So the first phase was Contract 1, and that was the lagoon decommissioning and sledge pumping upgrades. And then the second contract was the energy center and digester upgrades. The third contract was the secondary treatment for plants 3 and 4, a new Wastewater pumping station, and new headworks. And the fourth contract was the tertiary filtration upgrades and the new outfall. There is a consideration of a future contracts of sledge thickening and a new administration building and miscellaneous upgrades, but that's going to be further developed in a pre-design later this year. Other considerations that we looked at for dividing the upgrades into separate contracts included contractor time and space, and we also obtained a designation of projects from the Ministry of Labor in order to ensure that the region was not the constructor of any of these projects. We wanted the individual contractors to be their own individual constructors, and this was through the aid of several coordination meetings just to make this happen. Project schedules were developed during the site-wide facility plan, pre-design, and detailed design and construction. As we fast forward to 10 years later, we have successfully completed over 4 major general construction contracts, ranging from $10 million to $40 million per contract, and also 3 smaller construction contracts in the range of $500,000 to $3 million. And we're ultimately meeting the objective in improving the effluent water quality as set out for 2018. So the region also reviewed the procurement and goods and services required for each of the phases of the projects and contracts. We had to consider what, if any, equipment needed to be determined to further develop the design or confirm the size of the equipment to fit in the building footprint, or was there a long lead for the manufacturing and delivery of the equipment that could impact the overall construction schedule. Since we were governed by the regional purchasing bylaw, we needed to ensure that we had an open and public competition where we could name at least 3 vendors that could supply the equipment specified. So typically, if we had to pre-select the equipment, we would then obtain council approval for the procurement to purchase the equipment. Here are just some of the examples of the tenders that we had pre-selected vendor equipment, and we found that we typically pre-selected quite a few pieces of equipment, including centrifuges, gas membrane holders, linear motion mixers for the digesters, and the generator for the backup power. In the end, we actually had to plan for all of these tenders in advance of at least a year of the construction contract. We also pre-qualified the SCADA integrator, general contractor, and materials testing consultant in advance of tendering the overall general construction contract. The tendering period usually for any of those three major construction contracts took between 2 to 4 months to process. In the past, the region's procurement was the traditional paper bid submissions and open public tender openings up until this year, 2017. We have now moved to a new electronic bidding system where the tender documents and the drawings and the addenda are being issued electronically, and the bid submission is being submitted electronically instead of a paper copy. There are actually 40 public agencies in Southern Ontario that have implemented e-bidding, including the region of York, the town of Newmarket, Township of Wilmot, and Chatham-Kent. The overall feedback from internal and external stakeholders, including the construction associations, have been fairly positive and supportive. So here's just some screenshots of the region's procurement page, and there are benefits, many benefits to this new e-bidding system, which shows that it's like an online, it's fully online, and you can submit the bids online. There's a compliance checker that helps with better submissions for compliancy. There's electronic bidding and online addenda notices. Other benefits also include that there are virtual public tender openings, so you don't have to physically come to our office to hear the tenders. There's no more late bids and no more calculation errors. And the overall reduction to analyze the bids are much lower than the traditional way of the paper copy. It's also good practice to develop a tender checklist to ensure that all requirements of the tender are complete. So also, in order to successfully tender the construction contracts and avoid delays to the start of the construction, the region tries to generally obtain most of the approvals in advance of these steps. So there were several approvals we had to consider from a local, provincial, and federal level. Some of the approvals took anywhere between 4 to 12 months, and so we had to plan and consider this carefully in the overall schedule. Since the plant is actually located in a residential neighborhood, we wanted to keep the regional councillors and the public informed about the project progress and milestones. So we did this by having public pre-consultation meetings, notices to residents about the construction and trail closures, and we also issued an annual community newsletter about the project status. So this was a good way of communicating and showing transparency to the public for this project. We also wanted to have good collaboration with the stakeholders of the project, including region staff, operations, and the design consultant. So in Phase 3, we decided at the planning and detailed design stage to retain ACONNEX, which is a web-based cloud system. This helps facilitate a central project information management tool to share and upload documents, transmittals, and design reviews. This was a very helpful and useful tool when we were transitioning to the tender and construction phase of the project, because we were able to collaborate documents with the general contractor using this web-based cloud system. This allowed the team members to communicate via transmittals and emails and track project schedules and meetings and statuses for RFIs, shop drawing submittals, and change orders, payment certificates, and tracking commissioning plans and deficiencies. Now, there's also other types of web-based systems, such as SharePoint, but we found that ACONNEX was a better fit for our project needs. So this picture is Contract 2, which is the Digestion and Energy Center. And this contract was one of the most complex construction contracts since we had to maintain operations continuously during construction. The upgrades of the digester was a retrofit of the existing digester complex and adding a new addition to that facility. The work area was very congested with other structures and buildings and underground utilities. There was also TSSA requirements for constructing in a Class 1 Div 1, which is like a highly explosive area due to the digester gas, boilers, and heat exchangers. There was also a demolition of an existing building to make room for the upgrades. The Energy Center was constructed in a small footprint within the staff parking lot and was also located in the floodplain, which had its challenges. The outdoor enclosure for the backup generators was housed in individual containers to reduce the size of the new building and reduce the overall costs. The consultant for this project was AECOM, and the contractor was Maple Reindeers. So this project was just substantially performed just this February, and the construction took about 2 years to complete. So I guess there's just a break here, and if there's any questions out there to clarify about any of the background or the procurement process to date.
And we just have one question so far, but please feel free to add these to the chat box. But we had a question from Lloyd asking, it says that given the facilities in the floodplain, was flood protection improvement considered as part of the project? So I think you mentioned there was an issue of being in the floodplain, but specifically, was the flood protection improvement considered as part of the project?
Yes, we had to consider the floodplain, basically from the GRCA, which is the local authority of the Grand River watershed. We had to design the building sort of in a bathtub to elevate at a certain elevation above the regional floodplain. So it was a little bit more expensive, and we had to ensure all of the electrical equipment was above this floodplain as well. So that was definitely a challenge in working in and constructing in the floodplain.
Great, thank you. There's another technical question here. What was used for phosphorus removal?
For phosphorus removal, it's a chemical addition, which is ferrous chloride.
Ferrous chloride was added, okay.
Yeah, ferrous chloride is added at the primary clarifiers.
Okay, thank you. And there's a question on funding. It said that you had received Green Municipal funding for Phase 2 2 years after the construction. Can you explain how that worked?
Well, actually, like the date in which we received the funding was finalized in 2015, which was 2 years later. But throughout the design and the construction, we were keeping the FCM updated on the progress and as well as the funding requirements. So basically, once the project was substantially completed, all the paperwork was then submitted to FCM for their review, and just as the end result, you know, the final I guess receipt of the funding was processed and came through, you know, in 2015.
Okay, thanks. Another question came up. It says, this is from Lynn. Do you have an estimate of the cost savings of going the DBD route versus other options? And maybe explain what DBD is for all of us here.
It's the design bid build process. Well, I guess I can't really comment on potential savings because we didn't procure any or had the delivery model of any other type of design bid approach. But we felt that was probably the most economic way because we could control each of the phases as well as take a pause when we needed to review the design requirements or the design criteria. before the actual construction, or take a look at the type of equipment that we were procuring. And because if we did the design build approach as an owner, we would have less control of the overall design, the type of equipment that is being procured, and even the contractors that would be contemplated. So we felt that this approach, we were able to have some control at each of the phases, from the planning, the design, and the construction parts.
That's great. We'll have a chance for some more questions at the end of your presentation, so please feel free to continue.
Okay. So from the lessons learned from Contract 2 on the complexities, we learned that to consider planning the construction sequencing during the detailed design was very important, because our project team with operations needed to understand the plant constraints in keeping the digesters operational during construction, and to also have contingency plans during major electrical shutdowns in order to connect the new backup power to the plant. It was also anticipated that the construction was going to take about 2 years through the detailed design, and we went through a rigorous process of evaluating construction sequencing and realizing at that time we needed to add at least another year to the construction schedule in order to realistically complete the project. So, and another point that we also, in doing a detailed underground utility locate in advance of the construction and during detailed design, this also helped confirm the record drawings, because sometimes they could be out of date or incorrect or unavailable. So with the success that we had with Contract 2, the consultant and the region presented a paper at the Water Environment Association in Ontario in 2015 to summarize the benefits of the construction sequencing during detailed design. And I can just provide a comment overall with the construction sequencing and early planning. The project was successfully completed on time and within budget. So the fourth contract, which included the tertiary treatment, the consultants for the detailed design and contract administration was AECOM and SEMA. And before the actual construction started, a pilot study was conducted during the detailed design to select a vendor for the disc filters for the plant. 4 vendors were pre-selected to operate a 1-week pilot of their system, and the successful vendor was Aqua Aerobics. They were able to satisfy both the design effluent objectives and provide competitive costs. So attached is just some photos of the pilot study, as well as the current construction of the new tertiary treatment building. The contractor is a joint venture with Maple Reindeers and Ball Construction, and we expect that the construction will be completed later this fall. A new outfall was also constructed and commissioned last fall in 2016, and this was critical to complete last year due to seasonal and aquatic constraints of constructing in-stream river works. In southern Ontario, the work in the river is usually restricted between March and July during certain times for breeding and nesting season. So we ran into potential risks if we had any delays for high water seasons or flooding events. And this is just a picture of the new diffuser structure that was installed in the river, and the old existing outfall pipe and structure was removed. So as I mentioned, there was quite a few studies we had to do in advance, and the aquatic investigation area was done around the outfall. So this is the area of the existing outfall, and the investigation took place 100 meters upstream and 200 meters downstream of the new outfall. The new outfall is discharging treated effluent in a southeasterly direction, and the new diffusers are in place, and it is showing good results, and it's also flowing in the same direction as the river. And these are just some of the pictures taken from, potential the studies that we had to do as part of the outfall, the relocation plans and protection plans. It takes about a year to complete all the studies and investigations because we looked at the bird, trees, and aquatic habitat. And it took about a year to actually obtain the overall approvals in order to construct the outfall. These are just some of the best practices from the construction side of things. And this is just a picture of the current construction for Contract 3 of the new headworks and secondary treatment and clarifiers. Some of the good things that we looked at is keeping the project on track by having regular project meetings, a good communications protocol and management tracking system to track RFIs and approval logs, having regular construction photos just to see the progress and videos, as well as looking at scheduling monthly progress schedule meetings to then look at the resources and to help monitor cash flows. The contractor also provided schedule tools and weekly site reports to provide tracking their progress. The consultant for this project was AECOM, and the contractor is a joint venture with Graham Construction and Harbridge. We expect that this contract will be completed by the end of December 2018. So once the construction is then complete, the commissioning phase would start. However, the planning of the stages of the commissioning should actually start at the design stage by the consultant, which would help the contractor prepare the final commissioning plans. Commissioning plan meetings by the contractor should be initiated at least 6 months before the construction is completed because there are several steps to be undertaken at the actual commissioning. There could be also multiple dates of commissioning of various equipment and processes, and in keeping in mind that the overall objective is to ensure that the upgrades are operating as per the intent of the design. So here's just a couple of items and steps that are considered in the commissioning startup, which includes the factory acceptance tests prior to shipping the equipment on site, pre-start health and safety, tagging of equipment, whether it's a go or no-go, input-output checks that are done through the SCADA integrator, the final site acceptance tests, and the operator training. In the final testing and commissioning, there would be likely some final regulatory inspection tests and some pre-tests, such as for the water, like a water test or a performance test. And ultimately, we ended up choosing a 45-day continuous operation to acknowledge and recognize that the system was operating as it was intended from the outset. We also included a holdback on the contract to ensure timely submission of the record drawings and O&M manuals, as we have found that that is usually sometimes a bit of a lag from the contractor. And also at the time of substantial performance, we would want to obtain final site occupancy permits and the insurance and any final documentations to operations. Typically, there's about a 1-year warranty period after of the general construction contract once it's substantially performed, and this is to address any defects or deficiencies. For every contract that was completed, there was a new operations and maintenance manual. There are pros and cons of having individual manuals with each of the contracts because of the number of binders. We had approximately 40 to 50 binders per contract, which is pretty significant. We have to find space for to store all of these manuals, and it was really becoming difficult in the first 2 phases of the project. So we decided to make the manuals also in a digital format for ease of finding the information, but we were also still required to keep hard copies of all the manuals at the plant due to regulatory requirements. So in Phase 3, we decided to reduce the number of hard copies by providing O&M manuals electronically, which could be uploaded to a portable device such as laptops or tablets. We also decided to consolidate the O&M manual for a whole plant process instead of each construction upgrade, which would help operations to use the documents in a more efficient and effective way. More recently, in Ontario, the Ministry of the Environment is no longer requiring hard copies of the O&M manuals if an electronic copy is available for viewing at the plant. And also a final note is that the region is corporately addressing asset management with a new software system which will allow operations to easily track maintenance schedules and replace aging equipment. So here's an aerial taken. The first photo on the left was taken in 2012, sort of in the beginning when the upgrades were progressing, and in 2016, which shows a difference of lots of construction that has and changes to the plant. And the good news is that we've seen very positive environmental improvements from the aeration upgrades observed with decreased ammonia levels downstream and increased oxygen levels in the Grand River. So we've also seen significant improvement of the health of the fish populations in the Grand River. The region also anticipates that there will be continued improvement to the Grand River once the tertiary treatment is in full operation by the end of 2018. As mentioned, also the region has several smaller plants of the 13 wastewater treatment plants, ranging between 1,000 to 8,000 cubic meters of rated capacity. And this is just a picture of Preston Wastewater Treatment Plant, which is located in the city of Cambridge. And there have been several upgrades since 2012, which includes digester upgrade, sludge tank demolition, a new odor control system, and new primary purifiers. This is just a couple of the pictures of the final completion of those upgrades. Of those 2 particular projects, they were each in the order of about $3 million. The consultant for both projects was SEMA, and Finbelt and Newman Brothers were the other contractors that completed the upgrades. And just one final note about this project is that later this year, there's a third project that will be addressing some upgrades to the headworks and blowers with the addition of variable frequency drives for energy efficiency, and some electrical upgrades, including a new transformer station. In this project, we are going to be receiving federal funding, which is in the Clean Water and Wastewater Fund. We expect that the construction will start this spring and to be completed by next March 2018. So I guess I just want to thank you for listening, and I just want to thank the consultants that were involved with the phases of the Kitchener Wastewater Treatment Plant upgrades, as well as the contractors that were mentioned, as well as FCM for allowing me to present this this to you. And I hope that the presentation was helpful and provided some practical guidance to apply in your own wastewater municipal capital projects. Also, just my contact information is there should you have any questions later. Thanks.
Okay. Thank you so much, Joanne. We do have about 5 questions so far, and invite everybody, if you have additional questions you want to throw into the mix here. Let me start with a more general one. There's a question about who the stakeholders are in the project.
Well, the stakeholders, it would be the regional councillors, the region staff, and the public at large. The project team itself, including the design consultant. So that's sort of the broad comment.
Okay, super. Second question is around the tender models. And the question is, was there a clear choice between the three tender models, the DBB or the DB, and the third option?
Again, I think because the region had adopted or had had lots of experience of the design bid build model, and again with the ability to review information at the different stages of the planning, the detailed design, and the construction, that this provided the region with a little bit of more control compared to, say, the design build approach.
Okay. Third question concerns value engineering, and the question is, how did you use value engineering as a concept in this project, and what lessons did you learn?
Well, we applied the value engineering actually at the site-wide facility planning, as well as different stages in the detailed design at about 60%. We looked at they looked at optimization from an energy standpoint, and as well as reviewing the type of mixing systems for the digester upgrades, and as well as the number of clarifiers for the secondary treatment for the new plant 3 and 4. We looked at, tried to reduce some costs, and we found that we were initially going to go with 4 clarifiers for each of the plants 3 and 4 of the secondary clarifiers, and we actually reduced the number of clarifiers to 3, and that had a fairly significant, I don't have the actual dollar amount, but it was probably just under $1 million worth of savings in concrete. Another consideration in the value engineering was, again, the linear motion mixers, and from an energy and operations and maintenance compared to using jet mixing, we found that the capital costs were slightly less than using the linear motion mixers, but also the overall energy savings. We were going to save about $1 million in O&M costs. And one other final note is the tertiary treatment. We looked at sand filtration and compared that to the tertiary filters, and we decided, like, from the value engineering, that it was better to consider tertiary disc filters because we would not need an intermediate pumping station and additional tanks for the sand filtration. So that was, I want to say, that was almost maybe $10 million in savings in capital.
So some significant savings there by using that approach. Quite helpful. And that's the approach you could apply to any scale of project, it sounds like, right? It's not specific for a large project.
Oh, I would agree with you on that. We are actually using value engineering on one of our smaller wastewater facility upgrades, and that's because we, you know, thought that there could be some potential savings because we had some upgrades that we were planning over the next 5 years, but we didn't necessarily want to spend all of the monies up front, and we were able to look at it from a different perspective and trying to stage, kind of looking at Kitchener as sort of a model, but to kind of split the contracts into separate stages. So the value engineering was very helpful there.
Well, that's great, and I do appreciate sharing some examples of both the large scale and the smaller ones in your work, and again, a lot of transferable ideas here. Turning to a new topic around sludge. We have 3 questions related to how sludge was disposed, as well as how the outfall, the reuse of the outfall was considered. Could that be used for irrigation, for example? And also reuse of the nutrients. So kind of related, but I guess the output of the new plant and how that was used.
Because the Kitchener plant had storage lagoons, and they were constructed back in the late 80s, early 90s, that generated, of course, quite a few odors. And as the neighborhood started to develop with residential neighbors around the plant, there was a need to consider off-site treatment to anaerobically digest and to stabilize the sludge. So the Manitou sludge station was considered because it was a few kilometers away and it was in an industrial area. So we have a force main that connects from the plant down to this transfer station that transfers the sludge. And so through the wastewater master plan in 2007, it was decided to consider centrifuges to treat the sludge and to stabilize. The other part, too, was the fact that land application was becoming quite difficult because it's only seasonal. And so we had to consider a sort of a 365-day process instead of a seasonal process, which land application can be. And so going with treating the biosolids with the centrifuges seemed to be the way to go, because it could be operated all year round. And the final disposal that we are doing is at landfills, as well as I think it's in a mine in northern Ontario. We are actually in the process of a biosolids master plan currently, so we are evaluating further options to look at sludge stabilization and potential, nutrient removals.
Okay. I'm just curious, I saw a couple of the aerial photographs in the maps, but how close is the nearest sort of residential area to that plant?
Well, across the river, there is a well-built-up neighborhood, and actually at the entrance of the plant, there are houses that are built. So I would say they're very, very close to this wastewater treatment plant.
Okay, but you're able to maintain an appropriate level in terms of odor control, which is great. There's a question related to that, specifically about the Cambridge one, the one in Preston, and what was the nature of the odor control system there? What did you use in the Preston plant?
It's a bio-trickling system that was used to address the odors, and it is one that was just recently constructed to address the odors from the primary clarifiers and the headworks. The manufacturer was BioRem, so it was sort of a pre-select of that type of system.
Okay, thank you. We have two more questions so far, but one is around the energy system. Is there any kind of renewable energy system that helps the plant be self-sufficient, either auxiliary supply from maybe wind or solar, or is there a possibility of energy generation from the plant itself, or biogas, for example?
Well, actually, that's another phase that we're already in sort of the early stages. I'm not really involved in that project, but there is a cogen consideration, cogen facility for both three of the facilities at Kitchener, Waterloo, and in Galt. So that's looking at the renewable sources of energy, recycling and using waste gas to heat. Currently, that's what we are doing, is using the waste gas to heat the existing buildings and boilers and the digesters. But with this cogen, that will probably further facilitate more renewable energy sources.